Yes, let's learn what are colligative properties in a solution. Chapter number 1 of class 12 NCERT chemistry. What are colligative properties? Colligative properties are properties of the solutions. Property of the solution. We know that whenever a non-volatile solid is put inside, is put inside or dissolve in um, a volatile solvent, its vapor pressure lowers. The vapor pressure of the pure solvent lowers. Whenever a pure solvent has some vapor pressure, but when something is put inside it, or when a non-volatile solid is kept inside it or is dissolved in it, when a non-volatile solid is dissolved in it, its vapor pressure will lower. So we will be learning what are the relative, what do we mean by relative lowering of vapor pressure. Okay, the colligative properties of the solution means those property which depend on the quantity or the number of solid particles that you are dissolving in the solvent. The properties which are not related to the properties that do not depend on the kind of the nature of the solvent. It purely depends on the number of particles you're dissolving in the solvent to make the solution. So suppose there's a solvent and you're dissolving one solid, say solid A, 50 particles, and so because of that 50 particles, there are some properties, and those are called colligative properties. If you instead of dissolving solid A, you dissolve solid B with same 50 number of particles, then it will show the same kind of property. So no matter what kind of solid you're dissolving in a solvent, the property will purely depend on the number of particles that you are dissolving, the number of solid particles you are dissolving. Those properties are called colligative properties. The first property is relative lowering of vapor pressure. The vapor pressure of the solvent or the pure solvent will lower. And there is one more property called elevation of boiling point of the solvent. Then elevation of boiling point of the solution. Then freezing, the depression of freezing point of the solvent, and the osmotic pressure of the solution. So there are 4 properties that we'll be learning as colligative properties of the solution. The first property is relative lowering of vapor pressure. So the lowering of vapor pressure or relative lowering of vapor pressure is directly proportional to the quantity of the solid that you are dissolving. So there's a mathematical expression which shows the vapor pressure of the solution and the mole fraction of the solvent. And this one is according to the Rolle's law. This is actually the mathematical expression, the way we show the mathematical expression that according to Rolle's law. The Rolle's law says that for a pure solvent, for a solvent, its vapor pressure is directly proportional to its mole fraction. If the mole pressure lowers, its vapor pressure will lower. If the mole fraction increases, its vapor pressure will increase. The partial vapor pressure of the solution or of the solvent will increase. So the vapor pressure of a solution P1, where the solid is non-volatile, whatever you're dissolving is non-volatile. It will stay it will stay inside. It will stay in the solution. It will not turn into vapor. So it's non-volatile. Is equal to the product of the mole fraction of the solvent, the pure solvent, and the vapor pressure of the solvent when it is alone, of the pure solvent. So this one P1 naught will be more than the P1, the vapor pressure of the solution. Solution in sense, we have dissolved something. We have some solid is dissolved in it. In the pure solvent, some solid dissolves, so it becomes solution. So solution of the vapor pressure of the solution is actually the partial vapor pressure of the solvent itself. Just because something is dissolved in it, the solvent becomes solution, and whatever you dissolve is non-volatile. So whatever the vapor pressure of the solution is not because of the solute, it's because of the solvent. So either you say the vapor pressure of the solvent or the vapor pressure of the solution, they are same thing. Please remember this. In that solution, whatever solute you're dissolving is non-volatile. So it has no contribution in the vapor pressure of the solvent or of the solution. So mathematical expression is this: the vapor pressure of that solution, because you have dissolved something in that pure solvent, is equal to, is proportional to, actually it is proportional to the mole fraction of the solvent. Why the term mole fraction? Because there is not only there is solvent, there's solid also. So whatever is the mole fraction of the solvent multiplied by, actually the vapor pressure is proportional of the solution is proportional to the mole fraction of the solvent. When the proportional sign is replaced by the equal to sign, we put a constant, and that constant is what? It's the vapor pressure of the pure solvent at that particular temperature. So thus the loading of the vapor pressure. Now in the pure solvent, you have dissolved some non-volatile solid. So the vapor pressure of that pure solvent will lower. How much it is lower? So it will be a loading of vapor pressure is denoted by delta P1. How much it is lower? Actually, initially it was P1 naught. That means the vapor pressure of the solvent, it's of the solvent alone at that temperature. That's denoted by P1 naught, minus when something is dissolved, its vapor pressure will decrease. So what is the vapor pressure now? It's the vapor pressure of the solution, or the vapor pressure of the solvent is now P1. So its difference will be what? It will be loading of vapor pressure. What was the vapor pressure initially when it was a pure solvent, and what is the vapor pressure now when some solid dissolve? That difference is called loading of vapor pressure. Now, according to this equation, we have this P1, that is the vapor pressure of the solution, will be what? It will be equal to mole fraction, the product of mole fraction, this one, the product of mole fraction of the solvent, and the vapor pressure of the solvent when in its pure state. Just simply replacing P1, this P1 by this portion, the right portion over here. Fine. So when I take P1 as common, what remains? 1 minus x1, and 1 minus x1 is what is called x2. So what has come out? Delta P1, that is loading of vapor pressure of the solvent or loading of vapor pressure of the solution, is equal to what? The multiplication of the product of the vapor pressure of the solvent in its pure state and the mole fraction of the solute. So it's a relationship. So what we found that there's a relationship between the loading of vapor pressure. The loading of vapor pressure is directly proportional to the mole fraction of the solute. The loading of vapor pressure is proportional to the mole fraction of the solute. So there's a relation with how much will the loading of vapor pressure, how much will the vapor pressure lower in the solution. It depends on how much solute, how much the non-volatile solute that you are dissolving. That means it depends on the mole fraction of the solute. So this loading of vapor pressure is a colligative property of the solution. And what do you mean by relative? What is my relative loading of relative means what? Actually, this should not be okay. One, yes. When you move this on the other hand side, on the other side of the equal to, it will be delta P1 divided by P1. What is this? What is this called? This is called this what? This is loading of vapor pressure. When this is below this as a denominator, what does it become? What was initially? What was the initial vapor pressure as a pure solvent, and what is the loading of vapor pressure? And this is called relative lowering of vapor pressure. So relative lowering is what? It's like simply a comparison. It's a ratio of lowering of vapor pressure to the vapor pressure of the pure solvent. This relative lowering of vapor pressure is equal to mole fraction of the solute. So this is the mathematical expression of this state, of this first colligative property. the relative lowering of vapor pressure is equal to what? It's equal to mole fraction of the solid. So how do you calculate the mole fraction of the solid? It's nothing but the ratio of the number of moles of solid divided by total number of moles in a solution. The number of moles of the solvent and the number of moles of the solid. Now it's very interesting. Now for very dilute solution, see, we generally what will happen, we will take a solution with a large volume and a small amount of solid to dissolve. So the number of moles of the solid will be very less compared to the total number of moles of the solvent. So N2 is very small in number compared to the N1. The number of moles of solid will be very minute compared to the number of moles of solvent, because we are taking very dilute solutions. There is a large volume of the solvent and a small amount of pinch of the solid is dissolved. So the number N2 becomes insignificant in denominator. So we are removing the N2, the N2, only in the denominator, but in the numerator it remains. So it becomes N2 by N1. We're removing N. A large number plus a very small number, it will be just a large number. Suppose 1000 plus 1. Saying 1000 or 1001, it's same. There's not much difference. So that's why we are removing the N2 over here. So N2 is removed. It's ignored. What remains is N2 by N1. Now comes the real one, where it will be used in the mathematical calculations or the application, this relative lowering of vapor pressure. What is N2? It's the number of moles of the solvent, of the solid. It will equal to given weight, the amount of solid dissolved by the molar mass of the solid. And what is N1? Similarly, how do you calculate number of moles? It's just a ratio of the ratio of the given weight divided by molar weight. So given weight of the solvent is W1 and molar weight is M1. So M1 comes over, it becomes M1 by W1. So in this equation, so what do you have learned? On the left hand side, what is there in the left hand side? It's the relative lowering of vapor pressure, which is the ratio of the lowering of vapor pressure to the original vapor pressure of the solvent, is equal to W2 by M1 by W1. So there are 1, 2, 3, 4 quantities are there. They are the molar mass of the solute, and the weight of the solvent, and the molar mass of solvent. So in 4 quantities, and if you know the relative lowering of vapor pressure, then 1, 2, 3, 4 out of 4, if 3 are known, 1 can be calculated, provided you know that what is the relative lowering of vapor pressure through machines, to whatever instruments or devices if you can measure the relative lowering of vapor pressure, and you know, and it's an unknown, it is an unknown solid that you're dissolving, and you know the molar mass of the solvent, the weight of the solvent that you have dissolved, and also know how much you have dissolved, right? How much solid you have dissolved, you know the weight, so you can calculate the molar mass of the solid. Let's take an example. For example, say there's a solvent, right? There's a solvent called benzene, and its vapor pressure when it is pure solvent is 0.850 bar. Fine. So when something, suppose you are dissolving an unknown substance, an unknown solid which is non-volatile in it, and its vapor pressure becomes, then it's this one. Its vapor pressure becomes 0.845 bar. So what do you see? We say that there is lowering of vapor pressure, right? Its initial vapor pressure was this. When it dissolves some solid in it, its vapor pressure is lowered, and it has become 0.845 bar. Now you know that benzene, its molar mass is 78 gram per mole, C6H6. So you calculate the atomic mass of the molar mass of carbon is 12, and that of hydrogen is 1. So it becomes 78 gram per mole. So 1 gram of that means 1 gram of benzene weighs 78 gram. Now, whatever the weight of the solvent, the benzene, you know, there are 39 gram of benzene. This one, 39 gram of benzene. In 39 gram of benzene, you are dissolving 0.5 gram of that unknown solid. W2 is known. So now what we can do, you can calculate the M2, which is denoted by Mx over here. So this X is the unknown solid. So you can calculate the molar mass of the unknown solid, provided you knowing this one, relative lowering vapor pressure. How will you calculate? You calculate by splitting this from this P1 naught and splitting this from basically lowering vapor pressure. That is called lowering vapor pressure divided by P1 means this one, right? Then it becomes relative lowering vapor pressure. And then by replacing on the right side, you have this molar mass of benzene is the weight of the benzene, and you also know how much solid has been dissolved. The weight of the solid is 0.5 gram. That is unknown solid X Wx. So from this given data, you can easily calculate the molar mass of the solid, of the unknown solid. So this is the application of the mathematical expression of the relative lowering of vapor pressure. Hope you understood.